Our first keynote speaker of today's conference, Professor Dr. Habib-ur-Rehman Sahab, the Dean of Faculty of Civil Engineering, UET Lahore. Professor Dr. Habib-ur-Rehman did his PhD in Hydrology and Water Resource Engineering from the University of Tokyo, Japan. He has authored more than 70 publications, and his area of expertise is physically based distributed hydrological modeling, regional scale, soil erosion, sediment transport modeling, and much more. Please, sir. Sir. Mm-mm.
Okay, please let me know. Can you see the presentation?
Not yet, sir.
You cannot?
Yes,
No,
sir.
sir.
It is visible.
Is it visible?
Yes, sir.
It is visible.
Okay. Okay, thank you. In the name of Allah, the most beneficent and the most merciful, Honorable Chief Guest, Mr. Muhammad Mohsin Khan Leghari, Minister for Irrigation Punjab, and Honorable Vice Chancellor, UET Lahore, Professor Dr. Mansoor Sarwar, Respectable Director, Center of Excellence, UET Lahore, Professor Dr. Noor Muhammad Khan, Conference Coordinator, Dr. Kaleem Sarwar, and other faculty members, highly learned speakers, presenters, faculty members, and participants of the first conference on sustainable water resources management. Assalamu alaikum, Ohayo gozaimasu, Nehao, and good morning. I am highly thankful of Director, Center of Excellence in Water Resources Engineering, who has given me this opportunity to say something in this conference as a keynote speaker. So as this conference is on sustainable water resources, so I have selected a topic related to it. And the topic of today's talk is monitoring and modeling MAR techniques, means managed aquifer recharge techniques for sustainable urban water resources. This would be the sequence of my presentation. As we are talking about the sustainable water resources, but unfortunately in Pakistan, we have not thought of it as mentioned by Honorable Minister also. What we are doing in the urban areas, we are expanding urban areas. We are, destroying the agricultural lands, doing urbanization, expanding the urban areas. The city limits are increased. And what we are doing once we do urbanization, we increase the impermeable areas, and which reduces the infiltration rate towards the ground. So the groundwater reserve reduces. And what happens above and over and above it for the food demand, for the water demand of the occupants, then we install a lot of pumps, so which extract water from the ground. So what we are doing, we are sealing the surface of the land by making impermeable areas, some of the impermeable area, and then on the other hand, we are taking water. So which means what we are doing. So this is not sustainable way of developing urban areas or the cities or the housing schemes. In these, what we are doing, actually, we are making such that the groundwater extraction rate, we are always keeping greater than the recharge rate, which is going into the ground. So it means we are disturbing the natural groundwater hydrological balance. I don't say that don't expand cities. Please do expand cities. Do urbanization, but give due consideration to the groundwater hydrological balance. As we disturb the groundwater hydrological balance, or any natural balance of the globe, we human beings, we will be in trouble. And the same is happening as far as the water resources of the urban areas are concerned. So that's why we must think about the MAR techniques, so managed aquifer recharge techniques, which, for example, are the delay action dams, bank filtration, infiltration ponds, infiltration galleries, and recharging wells. One of the example is the large diameter recharging wells, which very rightly pointed out by the director, Dr. Noor Muhammad Khan, that those were installed in UET as well. And actually now I am talking about that, those four, the large diameter recharging wells, which were installed by the UET in collaboration with the LDA. And, after the installation, we have given an MSc research on it as the performance. We could evaluate it. And not only one MSc, a series of MScs are given on that topic. Anyway, this work which I am going to present, actually these are the research work of my two students at the Center of Excellence, UET Lahore. One is the Masood Ashik, who has done work on the monitoring and modeling of the groundwater recharge through these large diameter recharging wells. And another work is of the Fahim Aslam, who has, the hypothetically provided infiltration galleries in the model town, and then we simulated the effect of those infiltration galleries. Let us discuss few MAR techniques which we can use to manage our aquifers. This one first is aquifer storage and recovery. This is the same well which can be used as pumping well or recharging well. When it is used as a recharging well, it raises the water table. So storage, groundwater storage is being increased. And when we use it as pumping well, then of course there is a cone of depression. And the next is ASTR, aquifer storage and recovery. So here there is a recharging well, and here we have a pumping well. So the recharging well supplies water to this pumping well, and in that way we can keep our groundwater resource sustainable. The another option is the dry well, in which the aquifer is very deep, and this is the recharging well, and then this is the pumping well. So in that way also we can keep sustainable up to some extent. The another example is the percolation tank or delay action dams, and due to this water storage, the water will infiltrate here, and on the downstream of that we can provide a pumping well, and in that way we can keep this water table more or less sustainable. The another option is rainwater harvesting. This is the rooftop rainwater harvesting, and water can be collected in the tanks, as well as the over and extra water we can supply to the ground, and which will infiltrate and raise the ground. And then if we can do pumping, so it means we can go towards the sustainable groundwater table. The another example is bank filtration, like this, providing a pumping well or pumps along the canals or along the rivers, so they continuously get in water through seepage, and in that way groundwater remains sustainable. The another example is the infiltration galleries, in which we provide trenches, and those are filled with the gravels, and whenever there is rainfall, that water and the runoff is allowed to go into those infiltration galleries. The infiltration galleries have the voids between these big solid particles, and then that water seeps with time. Another example in the infiltration pond, like this pond, which are deep, parks, usually which you might have seen provided by DHA and the other housing societies. So whenever there is a rainfall, whole of the surface water comes here, and then from here water goes down and it raises the water table, and thereby and nearby there is a tube well from where we are extracting water. So these are the ways by which we can keep our ground storage sustainable. Now come to the specific research which has been carried out at UET Lahore. One is by providing 4 large diameter recharging wells. So what we have done, after the installation, only the recharging wells were installed by the NBA, but later on through an MSc research, we have also installed some equipment for monitoring the groundwater, that how much groundwater is entering into this large diameter recharging well. This is the section of the recharging well, and what it affects to the water table, the hydraulic grade line, and how it is raising the water table. So for monitoring, 2 piezometers were installed. So here, if you will see, these 4 are the recharging wells, and the idea is that this Junaid Jamshed Stadium is divided in 4 parts. The slopes are given in that way, so the water moves in these directions. So the water of this part moves like that, and here, and the large diameter recharging wells, they become effective when there is high intensity rainfalls, which produces the surface runoff. So once the surface runoff is produced, then that enters into these catch pits, and there is a sewer line here, and here is a sump. So the whole of this surface water enters in the sump, and with a pipeline, this sump is connected with this recharging well. And then in this way, water goes in that recharging well. So this is the inlet through which the water goes in the recharging well. So what happens? Whatever is the intensity of precipitation, water very quickly enters here and then is stored in this recharging well. And there are holes in the wall of this recharging well through which water moves in radial outward direction all around. And then this water table, the water level in the recharging wells comes down. And this is the working of the large diameter recharging well. These are very useful to avoid or to eliminate or finish the surface inundation quickly in the urban areas. And once the water is being stored here, later on, slowly it's keep on infiltrating and moving into the ground. These are some pictures during the development of the large diameter recharging wells. So this is the excavation, and this is the pad for the wall, and then here again you can see that the brick wall is constructed for sinking the well, and the well is. These walls are going down up to what depth we want to keep it. And then this is the masonry work which has been carried out with the holes on sides. And this is finally the recharging well. And these are the ladder and to go inside for the maintenance work. And in between, filter material was provided ranging from coarse aggregate from 1.5 to 5 inches diameter, because from here the water has to move in these lateral directions. And this is the cap or cover with this hole to monitor the level of water inside this large diameter recharging well. These are some pictures of the many catch pits, and this is sewer line, and this is acting as a connector as well. So water from the sewer line comes here and then enter here and moves, and this is a grating provided over it, as the large, the leaves and the other things should not enter into this catch pit. And this is the water sump, construction of the water sump, and this is the more later stage, and this is the final stage of the sump. So the water from the two directions comes here and is discharged towards the the recharging well. And these are the top slabs over here. After the construction or installation of these large diameter recharging wells in the Junaid Jamshed Stadium, what we observed on 3rd July 2018, there was a severe rainstorm of 252 millimeter of the rainfall, and this is the picture at 3 p.m. and you can see that after that rainfall event, this is the Annexi ground. So Annexi ground, there is a flood inundation and it's full of water, but due to these groundwater recharging wells, there is no water on the Junaid Jamshed Stadium. So that shows that how quickly these large diameter recharging wells were working, and with time that water actually moves in the ground and improves the groundwater level. The main objectives of this research work to install flow meter, as I already mentioned, that the equipments were not installed to monitor and are to check the performance of the these recharging wells. So Masood Ashik, so he installed flow meter and also two piezometers to monitor the groundwater fluctuations. The second objective was to assess the groundwater depletion rate without recharging well, and the third was to assess the groundwater depletion rate considering the recharging well. It means what is the improvement by providing recharging well. So this was the methodology adopted by the student. So he has collected data like rainfall data, groundwater data, in which that includes the water levels, pumping wells, and the recharging wells, number of recharging wells in the area. Then that data was analyzed in the form of temporal distribution of rainfall and the groundwater levels, and also the depletion rates were calculated using ArcGIS software. And then the next work was installation of the equipment. Nowadays this experimental work and the installation of equipment in the field, normally the student, they want to avoid. They only want to work on computers in the lab or in the computer centers. So I think I appreciate this student that he has done the physical efforts a lot. So the flow meter was installed to measure the volume of water which is entering in the recharging well, and also the two piezometer to know the position of the groundwater table. Then groundwater table positioning was modeled through using ModeFlow software. So without recharging well or also with recharging well, and the proper calibration and validation was carried out for the both cases. And then further, it was used to model the change in the groundwater depletion rate, to find the change in groundwater depletion rate. So this was the data which was collected for the research work, the topographic data from Google Earth, bore log data from WAPDA and NESPAC, daily precipitation data from the PMD, and the piezometric data from WASA and UET Lahore, and the pumping well data from WASA and the UET Lahore. This is the same area. So this one is our Junaid Jamshed Stadium, and this is the university area. And this one is the enlarged view, and this is the 1/4 of the Junaid Jamshed Stadium, which is enlarged here.
Sir, and you can see it's not visible. Now we are seeing your email screen.
Voice is not.
Shahid Saab have shared his screen. Sir, please unshare your screen. Shahid Saab. Please unshare your screen, sir. Habib sir, your screen is not visible. Your presentation is not visible.
Not visible. Okay, I will retry. Huh?
Please share again.
Oh, yes. I'm sorry. Where is that? Now, can you see slide?
Yes, now it is fine now. Yes.
Okay, thank you. All right,
And
we are back.
Your time is near to conclusion. Please show us your results.
All right. Anyway, and this is the data analysis, and it shows the position of the groundwater table. So in Lahore, about the water table is 50 meters below the ground surface. And you know, in this year, 2018, there were less rainfall, so the water table has gone down. And these are the plots of the water levels, the water tables in these two observation wells. And then the groundwater depletion rate was computed for these 3 years from 2015 to 2018. And the average annual depletion rate was computed as 0.81 meter per year. So this was the depletion rate without recharging wells, and it was minus 0.8 meter per season in winters, in summer season. You know, normally in summer season, we have less depletion rate. And this is in the winter season without recharging well, and the value was 0.84 meter per year. And this is the depletion rate of the groundwater table with recharging well. It was 0.5 meter per season in winter, so which is reduced. And this is the installation equipment, and particularly this is the flow meter, and here we can see the flow, how much has entered, and this is the final position. This is the pipe coming, which is supplying water to the recharging well, and here we can read the volume of the flow. This is the installation of the two piezometers to know the position of the hydraulic grade line, and this one is the pad, concrete pad, and the lock is provided as the other people, they should not disturb it. And you know, this one is the shifting of the levels to oversight from the benchmark in UET. And this is the modeling, and in modeling, the 7 stress feeders were considered. And this is the the model area with these details. So 20 by 20 meter grid was used for modeling. And in total, 12 pumping wells were added in the model, 5 of the UET and 7 from WASA. Then model was calibrated by using these calibrating parameters for the hydraulic conductivity that was within the range, and the storage parameters, those were within the range, and the initial head was taken as 174.8 meter. And varying head flow boundary condition was used in the model, and these are the results of model calibration. So these points lie on the 1-in-1 line. It shows that the simulated values are very close to the observed values. These are for all stress periods. And now this is the without recharging well. This is the contour map. And now with recharging well, it was modeled for all 7 stress periods. And the volume was calculated of the recharging well. Recharging wells, they have enough capacity because they are 15 meter diameter and 30 meter deep. So 150 cubic meter is the capacity of the recharging wells. But you know, the none of the rainfall was so high that it could only fill 28%. So then this is the calibration with recharging wells, and those are within the 95% confidence limits. Again, these are the results for validation. And this is the performance of the recharging well. This is a recharging well. This is the observation well 1 and observation well 2. What has happened, due to this infiltration of the water table has risen from this side, and the slope of the water table is reduced now. And these are the depletion rates for summer. Without recharging well, it was minus 0.72, and in winter it was 0.84 meter per year, whereas on average year basis it is 1.02 meter. But in winter season, as were having the data of winter, so the recharge rate was, the depletion rate, groundwater depletion rate was reduced to 0.45 meter per year from 0.84 meter per year. The next work was of the infiltration galleries, which are trenches which are filled with the boulders, and it gives enough space for water. So whenever there is rainfall, that comes here and then moves in the lateral directions. And this is the pictorial view of the infiltration galleries. And that infiltration galleries were provided hypothetically in the model town area. So this is the distribution of the total model town area. Residences are about 56%, commercial area 2%, roads 19%, nurseries 4%, and green area is 19%. So I think the model town is a housing society which has maximum green area in Lahore. So 19%. And now, so the location, if you see this in this color, in this color, what is that color? Blue. And these are the locations of the infiltration galleries. Actually, these were provided where there are depression points, where there are green belts along the roads, on the side of the parks, and on parking lots. So total 180 infiltration galleries were proposed, and they were covering an area of 4.3 hectare only. And this housing scheme have 592 hectare total area. And these are the selected locations for the infiltration galleries. And then he has done modeling, and the results I am just giving you in the concluding remarks. So large diameter recharging wells in the study area have reduced the average groundwater depletion rate by 0.39 meter per year, considering the winter data. And the groundwater depletes more rapidly in winter as compared to in summer. So it means these were working very efficiently. So infiltration galleries in the study area have reduced average groundwater depletion rate by 0.15 meter per year. So large diameter recharging wells are more effective in reducing the groundwater depletion rate and flooding on these surfaces due to large capacity of the recharging wells. Small diameter recharging wells locally rise the water table and are not much effective in reducing the flooding on the surface, because the water goes in the pipe in the well very slowly. And number 5, clogging of the filter material is a serious problem in recharging wells and infiltration galleries. So we have to do annual cleaning of it before the monsoon season. Infiltration ponds, which are deep parks, to which in Urdu or in Punjabi we say dungi grounds, are the cheapest and the most effective means of groundwater recharge with practically no maintenance cost. And these are the final recommendations based on these two researches. Number 1, large diameter recharging wells are recommended with certain modifications to recharge groundwater and manage flooding. So it has dual purpose. The second is infiltration ponds. Deep grounds are recommended for quick urban flood management, and groundwater recharge being most economical solution and almost no maintenance cost. And the third recommendation is that groundwater hydrological studies must be carried out before developing housing societies to propose suitable MAR techniques, and it must be made part of the policy document. As Honorable Minister is also with us, and I would emphasize the need of the hydrological report, which the main purpose of this report should be that the groundwater hydrological balance should be disturbed as minimum as possible by providing recharging wells, by providing infiltration galleries and those old designs. So that should come with to LDA or CDA before approval of the housing society. So with that, I conclude my presentation. So thank you very much for your patience and listening.
Thank you so much, sir, for sharing your valuable knowledge.